Okay, so we're going to crack on now. We've finished mesh analysis and we're going to be moving on to superposition theorem, which is it's an interesting one. My lecturer, he said that this is the main one that I'm going to be using in my second year, so it's very, very important that I revise this one. All right, so we've done nodal, we've done mesh. Let's go on to superposition theorem. Okay, so in terms of the actual definition of superposition, it has to do with a circuit that contains more than one independent source, whether it's voltage or current. So you've got obviously a battery, or you've got a voltage source, you've got the current sources. So any circuit that has more than one of these, then what we're saying is that the response in any of the branches, meaning like the currents and voltages, it's equal to the algebraic sum of all of the other responses caused by each individual source when it's acting alone. That's the important part. So, and that's obviously on the basis that all of the other sources are replaced. So that might not make any sense to you. Don't worry about it. It'll make sense when we go through the example. So let me draw an actual example. So you've got a battery, another battery. Let's go down here. You got a resistor here, resistor. So R1, R2, R3, and you got V1, V2. So the way that you would work out the voltages and currents in this circuit here, a nice and easy way to do it is to basically take the whole circuit again. Let's duplicate it twice. All right, and so what we're going to do is we're going to remove the voltage sources. One thing bigger. Okay, so now what we're saying is that this circuit up here, in order for you to find the voltages and the currents in all of the branches, all you have to do is take these two circuits, this one, and add them together, right? So what you're doing is you remove this voltage source here, and you remove this one here. And what you do is you work out what I1 is here, what I2 is here, what I3 is. Do the same over here, I1, I2, I3. Then all you got to do is just add them together. And this main circuit up here will be the algebraic sum of these two down here. It's one of those ones where it's super obvious if you think about it. And if I asked you to work out the voltages of this circuit without you knowing any of the other skills, your mind would probably come to it anyways. You'd probably think about it and go, you know what, yeah, I could just do this. Just remove one of the voltages, calculate what the current is in there, then remove this one, then calculate the current now in this one, add them two together, and you got a total current. So if that still doesn't make sense, don't worry about it. It will start to make sense when we go through it. So let's go through the steps. Can you take a guess at how many steps there are to do when you're doing superposition? If you've watched Nodal and Mesh, then you know that there are 6 steps to solving it. There's 6 steps to solving mesh, 6 steps to solving nodal, and again 6 steps to solving superposition. Now these, the 6 steps thing is something that I've mostly come up with. It's not. I mean, you could technically make it 7 or 8, but in my mind it's easier for me to remember. Sorry for all the Christians out there, but 666. It just makes it easier for me to remember that. There's 6 steps for nodal, 6 steps for mesh, 6 steps for superposition. All right, cool. So, number 1, first step is to solve all currents, and that's for each source. For each source, by source I mean voltage or current source, and the only way you're going to do that is by setting all other sources to 0. And I'm going to expand on this point, setting all other sources to 0, in a bit. All right, so number 2, you're going to simplify the circuit, and you're doing that to get the total resistance. So you simplify the circuit to get total resistance. All right, so you're just going to use basically V equals IR, and you're going to use the parallel resistance series equations to work out what the total resistance is. Then number 3, you're going to calculate the total current, meaning the total current. Oh yeah, I can't spell. The total current coming out of the battery. So calculate total I, or I total, and then V total. but obviously you're going to know V total from R total. So that's basically V equals IR, right? Then after that, number 4, you're going to do the current or voltage divider. If you're not sure what that is, go back 3 videos, we covered that. The current and voltage divider for each branch. Then you're going to basically repeat all of the previous steps. So you're going to repeat, let's put repeat steps 1 to 4 for all sources. So basically, once you've removed this voltage source here, you've removed it, then you do all of the calculations. Then you come over here, you remove this one, and you do all of those steps again, right? Okay, and then finally number 6, once you've done all of that, then you add. So basically, like we said, the algebraic sum of all of them, add all the currents together, and that will give you total currents. So add all currents together for total currents. Cool. Let's make these steps a little bit smaller so they fit onto this page. Cool. A bit smaller again. Okay. Alright, so I need to make probably there's probably 3 things that we need to keep in mind really. I'll cover this again when we do the example, but I just want to mention it separately because it is very, very important to remember. Okay, so in terms of when adding total currents, so right, when you're doing the last step, focus on original current direction. What I mean by that is that in the beginning we're going to label currents. So we're going to say this one's this way, that way, that one that way. So what we need to do is we need to focus on the original current direction that we put. And the important point is if it's the same direction, right, then add. You add the 2 together. If it's opposite direction, then obviously you do the opposite of adding, then you subtract. Again, if this doesn't make sense, don't worry about it. We're going to go through a whole example anyways in which it will make sense. And an important point when it comes to labeling, let's put when labeling directions, basically the battery is going to force the direction. So for example, when you remove this voltage source, you've got positive, negative here. So current's going this way. Don't then label it that way once you've removed it, right? Because we already know current's going the opposite way because this is the positive terminal of the battery. And since in this circuit here, this whole circuit here, there's now only one voltage source. So there's no, it'll be funny, but there's no way current's going this way, right? In this particular circuit. Up here, on this main circuit, it might be, and you could draw it going that way, that's fine. But when you're doing this circuit here, you know, it's funny, but I'm laughing because I've done it before. Don't draw the current going into the battery. That would be weird. Okay, so when labeling directions, battery or voltage source, whatever, voltage source forces direction or dictates direction. Okay, and then probably the most important point here is that so how to set to 0, how to set sources to 0. So we put it in our steps, right? We've said that we're going to set all other sources to 0, yeah? So what that means is you're removing the impact that a current source has on a circuit, and you're removing the impact that a voltage source has on a circuit. So if we've got a circuit with 10 volts and another component in it with 2 amps, right? So imagine this is a circuit, right? You had R2, R1. If you wanted to remove the impact of this, you'd be setting it to 0, right? And so there's a way, the way that you set that to 0 matters. So let's touch on that now. So if it's a voltage source, right? So let's say I'll use this. Let me use this example. Like what we've put here, right? If you wanted to remove the voltage source, then what you're gonna do is you're gonna replace it with a short circuit, right? So what that means is you take your voltage source, rub it out, and then you just put there like that. So you make a short circuit. Or another way to do it would be, for example, to do like this, if you can imagine that. Alright, so let's do the same for current. So if you wanted to now remove the current source, the way that you'd do that is you'd remove it and you replace it with an open circuit. So with current sources, you replace it with an open circuit. Okay, if that doesn't make too much sense, again, don't worry about it. But basically, in terms of the voltage sources, a voltage source like a battery or whatever, its internal resistance is 0, right? So then you're replacing it with a short circuit, because a short circuit has 0 resistance, obviously, right? So when you make this line here, then there's no resistance here. So similarly, a voltage source has no resistance. So the way that you remove it from the circuit and it having no impact is by replacing it with a short circuit. And for the opposite, for a current source, its internal resistance is going to be infinity, as high as possible. So in terms of having an infinite resistance, if you had an open circuit, then no electricity can flow through it. Basically, if you had a circuit and then you cut the wire, now between the two pieces of wire is just air, right? So even though air doesn't have an infinite resistance, but yeah, you basically have an infinite resistance in terms of the electrons inside that wire. They're not jumping across through the air, right? So even though they could, obviously, but basically you have an internal resistance that's equal to infinity. So you replace it with an open circuit. Cool. Okay. So if none of that made sense, don't worry about it. Let's just do the example, and then that will just start to make sense. This is just how these things are, right? Okay, so let's draw a funky circuit. All right, so you got battery. Should probably draw it bigger, but it's fine. Let's do a battery here again, and then standard resistors here. Just basically like the mesh one, but with 2 sources. Let's flip the battery, because I don't think we've done an example of the battery being flipped yet. So imagine you had it like this. So this is the positive end, that's the negative. Positive, negative. Okay. So don't get put off by seeing a battery source flipped or upside down or whatever. It doesn't make a difference. So don't let that put you off. Okay. Alright, so let's get our steps first, which we had written down. Where are they? Over here. Okay, so what we're going to do is, let me actually give everything a value. Stick to the same 10 volts, 6 volts. Let's go R1, R2, R3, and I don't know, 20 ohms, 20 ohms, 40 ohms. I think this is the same as what we did last time. So now that we've got a full circuit, what we're saying is let's find out the current and voltages for all of the branches in this circuit. Cool. So the way that we're going to do that, step 1 is we're going to solve all currents for each source by setting all other sources to 0. So we just need to remove one of these voltage sources. I actually didn't put on here as part of the steps labeling everything. It's very, very important actually that we label. Usually I include labeling as part of the first steps. But yeah, so basically what we need to do is we need to label which direction we're guessing that the currents are going before we do anything. So if you assume, for example, that this is the positive end of this battery and the electrons are going this way, right? And so through R1 that way, and then let's say coming back down R2, and then let's say this 10 volts is sending electrons that way. So now we've got the direction for all of the resistors. So we're saying that this is positive, this is negative. We're saying this is positive, this is negative, and this is positive, negative. Cool. Okay. So that's an important step in terms of when we add everything up at the end. That's an important point to do. Okay, so now let's remove one of the voltage sources. So we'll just copy and paste this. So let's put part 1, and then let's remove 10 volts. Okay, so we're going to remove this one, and we're going to replace it with a short circuit, remember? So like we said up here, voltage sources are replaced with a short circuit. Okay, so we've removed that one now. Now when we're looking at this circuit here, remember, like, we've got the battery upside down, right? So we could, for example, if you wanted to, you could turn it on its head like that. Right, and then even if you, as you're looking at that, for example, you can see that this, if you said it, the electrons are coming this way, going this way, right? And they're coming this way, going this way, right? Because they're going to come up here and they're going to split left and go right. So you can actually see, and then, you know, they're meeting back here and going this way. So you can actually see that these, another way of drawing this circuit, if you wanted to, would be to do this. You got the battery this way, and then you've got resistor, resistor, and resistor. And so you can actually, so all I've done is I've just moved these resistors up to here basically. And then what you can clearly see is that these are actually in parallel. By these I mean these two side resistors, which I think we've labeled, what's the middle one's R2. So let's label that R2. This is 6 volts, right? 6 volts. Yep. And then each one of them is R1, the other one's R2. What's the value that we put for R1 and R2? The R1 is 20 ohms. R3 is 40 ohms. Wait, which one's R3? This is R3, right? 40 ohms. Yep, and R2 in the middle is 20 ohms. Okay, so when I'm saying that they're in parallel, I'm saying that R1 and R3 are clearly in parallel. Obviously, in terms of, if you think in terms of, always in terms of electrons, let's do some electrons firing out of this battery. So when they're coming up here, they're then going to go this way and this way. So you can see that the electrons will be being split between these two resistors. So we know that R1 and R3, this is how we write R1 and R3 are in parallel together. So if you remember the parallel equation, it's the product over the sum. So we can find out the total resistance for over R1 over R3, which is going to be 20 times 40 divided by 20 plus 40, which is going to be equal to 2 times 4 with 2 zeros, 800 divided by 60, which is 80 divided by 6, 13.33 ohms. So now you have a new circuit here basically of battery, resistor, and then you have this combined resistor here. So you got 13.33, and you got 20, and then you got the 6-volt battery. So you can see by looking at this one here now that these two resistors are now in series. You simply just add them together and you end up with a circuit like this. And that will give you 20 plus 30, 13.33, which is 33.33 ohms. So we know that now the total resistance for this first circuit, which we can call it 1, but we can say, let's call it A. So we know that RA is equal to 33.33 ohms. That's my dodgy ohm sign. Alright, and so we know that VA, which is the voltage, right, for this circuit, is 6 volts, right? Because it's the only voltage source. So that means we've got 6 volts. And so then we can work out IA, meaning the total current coming out of this here is going to be what? VA divided by RA. Or you could say 6 volts divided by 33.33. And that would give us the total current. So let's do that. 6 divided by 33.33. And that gives us 0.18 amps. Right? So now we have the total current, we have the total voltage, and we have the total resistance for this circuit. So now what we need to do is we actually now need to work out, we're not done yet. So we know that 0.18 amps are coming out of the battery. Now we need to continue around this whole circuit and figure out how much current is going down here, figure out how much current is going this way, that way, right? Okay. Also going this way and down there. So the current's being split this way here, and it's being split into thirds basically. So if you can see that there, the ratio here, one resistor is 20 ohms, the other resistor is 40 ohms. So what we know is that 0.18 amps, most of the current is going to go to the lower resistance, right? Because obviously electricity flows where there's a lower resistance. So if it has a choice between how much of it is going to go to the 20 ohm one versus the 40 ohm one, the ratio here between these two numbers is a 2 to 1, right? So the trick when you're using like ratio is to know that the higher amount of electricity is going to the lower ohms. So we know that, for example, if you divide 0.18 by 3, that would give you 0.06. So we know that 0.12 amps is going to the 20 ohm one, and 0.06 amps is going to the 40 ohm resistor. So this is the unconventional way of doing it, and this is how you do it if you wanted to do it in your head quickly. If you want to do it the legit way, then the legit way to do it would be to use a current divider. If you can't remember what the current divider is, let's go through it quickly. So you got I1 is equal to R2 divided by R1 plus R2, and then all of that times I. What we're saying there is that there is the current through R1 here is going to be equal to R2, which is obviously in this instance here, this is R2, right? But in terms of the current divider, we're talking about this split that comes this way when it's getting split that way and that way. Then for the purpose of the current divider, we're talking about R3. Maybe we could just make it R3 for simplicity. So we're talking about the value of the resistor we don't want. So we can say, for example, the current in I1 is equal to the value of the resistor we don't want, which is 40, divided by the sum of the two resistors, which is R1 and R3, which is 20 plus 40, and then times that by the input current, which is 0.18 amps. And so we could work it out like this by saying 40 divided by 60, or 4 divided by 6 times 0.18. 4 divided by 6 is also 2 over 3 times 0.18, and then so 2 over 3 is going to be equal to 0.112. And so I1 is equal to 0.12 amps. And so as you can see here, did the same thing here. So this is like the unconventional way of doing it. You'd get used to doing it like this. Just in terms of ratios, you can clearly see that the current's being split. Imagine if they were both, for example, 20 ohms, you would just know that, okay, the current's being split directly in half. You wouldn't need to do the whole current divider equation, but it's fine. We can do it anyways. It's good revision, isn't it? So now we have the values of I1. We know that I1 is equal to 0.12 amps. We also now know that I3 is equal to 0.06 amps. So now how do we find out I2? So just obviously know that, current's not being used up in the circuit, right? So the currents coming, both, you've got 0.06 amps coming this way, you've got 0.12 amps coming this way. They're both meeting up here and they're coming down this way, so we know that they're just adding together, and that gives us 0.18 amps. So we know that 0.18 amps is in I2. And so the only thing now to remember is that here these I values are for circuit A, right? With this circuit here where we've removed the 10-volt voltage source that was there. So now we're going to do the exact same thing for circuit B, and then when we've got our I values for circuit B, we're going to add these two together, and that's going to give us the total current which actually exists in this main circuit here. Cool? Okay, so now let's do the exact same thing, but this time let's do B, and we're going to remove the 6-volt source. Okay, let's copy our circuit. Okay, let's remove 6 volts. So again, since it's a voltage source, we replace it with a short circuit, and then now we've got our 10-volt circuit, and we know now that let me just remove some of these. Okay, so we've labeled these blue arrows here are for the original current direction that we chose. But now in this situation here now, because we're talking about, remember like I said that the battery forces the current direction, so we know that this positive terminal, these pink arrows represent the current direction of this B circuit. The blue one represents the current direction of the actual circuit. But we've removed that 6-volt source now, so we're just talking purely about this B 10-volt circuit. So we've got the current through R3 going this way, which is what we put last time, and we're gonna have this current going this way, which is the same. However, the big difference here now, and this is where you can go really wrong, there's no way in this circuit the current's going that way. It's not happening for R1. The current is going to come to this point here. Some of it's going to go this way and some of it's going to go this way. So the current direction here through R1 is the opposite. Very important point. It's the opposite for this B circuit. Cool? Okay, so let's do this then. I forgot to go back and do or mark off my steps. So we're solving currents for each source, and we're setting all other sources to 0. We've simplified the first circuit by finding the total resistance. Then we calculated I total using V equals IR, and we did the current voltage divider for each branch. And now we're repeating step 1 to 4. So we're going to simplify the circuit again and find the total resistance here. Okay, so let's just redraw the circuit so we know what we're looking at. Okay, so this is the circuit. You got R1, you got R2, and R3. So what you can see is that electrons, they're coming out of this battery here. They're going through this one, and then when they get into here, they're splitting this way. So we know that basically you could redraw this whole thing as, you could put R1 here, and as you can see now, you can clearly see that they're both in parallel, right? So we know that R1 and R2 are in parallel with each other. So we just do the exact same equation that we've been doing. So they're both 20 ohms. So actually, we don't even need to do much here. If you got two, okay, I'm gonna do it. Let's just do it anyways, because I'm just thinking if this is your first time, I don't want to add any more than you need. Even though I would really recommend that if this is your first time, don't watch my videos if it's your first time, because I'm revising as a second-year student. I'm not a first-year student anymore, so this might be blowing your mind. Go back and watch. Although, you know what? Funny enough, a lot of the videos on YouTube I found super confusing. So if you're like me, go. I don't know, man. Go. Yeah, I don't know what to do. Sorry. Okay, so let's just do the standard product over sum, because they're in parallel, right? So we can just do product divided by the sum. Right? So we've got 20 times 20, because these two resistors are 20 ohms each, over 20 plus 20, which is 2 times 2 is 4, and then 2 zeros, and then over 40, and you can scratch out this 0, so you've got 40 divided by 4. 40 divided by 4 is equal to 10. So you've got a 10 ohm resistor basically. I'm really dying to tell you something here. You know, the shortcut of doing all of this. I'm gonna say it, and if it confuses you, I apologize. But basically, when you have two resistors in parallel and they're the same value, the value is always half. Right? Think about it. So it's always gonna be half, basically. Just keep that in mind. All right, cool. So let's redraw the circuit that we've got now. Then, so we've got the battery, 10 volts. We've got a resistor here, and then now we've got a new resistor here of 10 ohms. And what was this one? 40 ohms and 10 volts. So now these two are in series, so then we can now add them together, and that gives us one resistor of 50 ohms and 10 volts. So we can say that RB, meaning the total resistance value of the circuit B, is equal to 50 ohms. All right, and we can find out, we know that the voltage B is 10 volts, so we can now find out IB, the total current coming out of the battery for this circuit, is going to be V divided by R. All right, so you got 10 divided by 50, which you can just remove that, so you got 1/5, or 0.2 amps. Yeah, cool. Okay, so now we know IB is equal to the total current in the circuit B coming out of the battery is 0.2 amps. So now we can take this whole circuit here, going to clean it up a little bit, and then we can use our current dividers to work out what the current is in each of the branches. Let's clean this up. Okay, so we know that 0.2 amps is coming out of the battery, right? So we got 0.2 amps going through here. So we know that I3 is equal to 0.2 amps. And then we've got 0.2 amps coming here, and we know that, look, both resistors are 20 ohms. That means that the current is going to be split directly in half between these two branches. So you're going to have 0.1 amp going this way and 0.1 amp going that way. So we know that I1 is equal to 0.1 amps, and we know that I2 is equal to 0.1 amps as well. Cool. And that's it. We've got our current values for the circuit B. Now we just need to add circuit A to circuit B, and then we have our total currents in all of the branches for our original main circuit, which, if you've forgotten by now, is this circuit here. Now let's go back up to the important points which I asked you to remember earlier. As I mentioned here, you're not just adding them together. Why? Because what I'm saying here is that when you're adding the total currents, you have to focus on the original direction that we set, which was here. You see these blue arrows? We set the original direction that we're saying that the currents are going. So when we're adding them together, we need to stick to that. Very, very important. So if they're the same direction as what we set, then we add them together. If they're the opposite direction, then we subtract. Very, very important point. I actually made a mistake on this on my exam as well. So let's just go through this. Let's just do it now so you can get the hang of it. So what we're saying now, to finish this off, is that I1, I2, and I3. And so now we're not talking about, we're talking about the total for the main circuit. So we can say I1 main, for example, I2 main, I3 main. This is for the main circuit, is equal to, and then what we can do is let's take a look to see if IA, so there's the current in I1A. So the current in I1 on the A circuit is in the same direction as what we said originally, or it's in a different one. Remember, we determined it based upon the battery, right? So we've got I1 over here. And as you can see, we've drawn it in purple as being in the same current direction as what we put in blue, which was the original direction that we put. So we can say that it's plus 0.12 amps. Okay, so that's I. So you know what, actually, let me just do it and go up a step. So plus IA1, right? Then now we're going to look at B, and we're going to say, is our B current, which is this orange one, is it going in the same direction or the opposite direction of R1? And so as you sorry, not of R1, but of the original direction that we set originally. And as you can see, the blue arrow is going the opposite direction. So we're actually going to minus IB1. Cool. I hope that makes sense. So same for I2 now. We're going to check, is our I2 current direction, is it the same as the blue? Purple going down, blue going down, so it is the same. So we're going to say plus IA2, and then we're going to check our second B direction, and as you can see from the orange, it's going down, same direction as the blue. So again, we can put plus IB2. And then now finally I3, let's check the main direction. So as you can see over here, purple and blue are both going the same direction. So that means that we've got plus IA3, and then check R3 over here. So our I3 is going in the same direction. So we've got plus IB3. And there you have it. So now we can just substitute in those values. So IA1 was 0.12 minus IB1, which was 0.1. And that, okay, we'll do that in a minute. And then so IA2 was 0.18 amps. And we're saying plus 0.1 over here. Okay, and then we've got IA3, so 0.016. 0.06. Did I say 0.016? 0.06 amps. And then plus IB3, which is 0.2 amps. And then now, so we can say that I1 is equal to 0.12 minus 0.1, which is 0.02 amps. And then we've got I2 is equal to 0.18 plus 0.1, which is 0.28 amps. And then we've got I3, which is equal to 0.06 plus 0.2, which is 0.26 amps. And there you have it. Now you have the total currents for all of those branches in the original circuit, which is this circuit here. Which is amazing, you know. I get a lot of satisfaction when I finish that. So what we're saying here is that I1, so the current going through, and also a good point to mention here now is that if you had a minus, if this was minus, what that would mean is that the current direction that we picked was incorrect. So we actually picked the correct current direction for all three currents for these. So if we look now at I1 here, what we're saying is that 0.0, was it 0.02? Yeah, 0.02 amps of current is flowing that way. And I2, 0.28 amps is flowing that way. And I3, then 0.26 amps is flowing that way. If you didn't do it like that, I don't know how you would come to this. But look at that. That's absolutely amazing that, you know, and if you think about it, it goes really. It makes sense. You would expect if you think about it, it goes really. I mean, if I built this circuit on multisim, I would expect that little current would be going this way. I wouldn't expect that there'd be a large amount of current there, and it fits perfectly. So yeah, so that's it. That's it for superposition. It might seem complicated, but it's not. It really isn't. And you know, like I said, I've been advised by my my lecturer that this is something that I need to be very, very comfortable with. So I enjoy it. I like it, and I hope you liked it too. If you liked the video, give it a thumbs up. And in the next one, we're going to move on to Thévenin's theorem. So yeah, thanks for watching, guys. I'll see you in the next one. Peace.